Hi everyone, welcome to Learn 24. So we are looking into the chapter Current Electricity, and the first topic that we will be dealing is electric current. So what is electric current? Consider a charge Q. If this charge is in motion, then it will produce electric current. So charges in motion constitute an electric current. So consider a conductor. This conductor has infinite number of charges flowing through them. If I am taking a particular area, I will be measuring the charge that is obtained there per unit time. So we can also define electric charge as the flow rate of charge. Flow rate means divided by T. So charge divided by time gives the mathematical representation of electric current. Also, we can calculate electric current in case of instantaneous as dq by dt. So that's the mathematical representation of electric current. So I have told you the fact that when charge is in motion, it will produce electric current. So we know that in case of conductors, there are infinite number of free electrons that are present in it, and they are in motion. But they do not produce electric current when they are kept as isolated system. Why? Because even if the charge is moving, it will produce an electric current, but it's moving randomly. So the net electric current will be always zero in the case of conductors because they are moving randomly. So their net electric current will be zero. Okay. So how can we help the conductors to contribute in electric field? We have to take this particular conductor and give it an external electric field. So when an external electric field is applied to a conductor, what happens is the electrons that are present will take place in the electric current field. Clear? So that's how electric current is produced with the help of external electric field. So we can only get electric charge to take part in electric field when we are providing an external field. Now let's look into the terms that are associated with electric current. The first one is drift velocity, and it is represented as Vd. So drift velocity is the velocity attained by the electrons that are present inside the conductors when an external electric field is applied. So drift velocity can be mathematically represented. So let's look into it. From the second law of Newton's motion, we know that F is equal to ma, mass into acceleration. So in case of conductor, the mass it is having is the electric charge minus E, and the force it is, or the acceleration that it is given is by the electric field capital E. So we got ma is equal to minus EE. Now if I am taking this ma here, so I can get A is equal to minus small e capital E by m, where capital E is the electric field. Okay, now consider the equation of motion V is equal to U plus AT. Here initially the electrons do not have any velocity, so U is 0. So our equation, the velocity approximate to this electrons is Vd, or drift velocity. So Vd is equal to, instead of A I am writing minus EE by m, and instead of T I am writing tau. Tau is the relaxation time. It is the time taken between two successive collisions of the electron, and it is calculated to be 10 raised to minus 14 seconds. So we got the expression for drift velocity as minus EE tau by m. So this is the mathematical representation of drift velocity, and you need to study it because it's needed in the upcoming derivations. Moving on, we are going to look into the next topic, which is mobility. So mobility means to travel or to mobile or to transport. So how are the transportation happening? It's due to the drift velocity. And how is it driven? It is driven by the electric field. So we can define mobility as the magnitude of drift velocity per unit electric field. So Vd by E is the general equation of mobility. We know that Vd is equal to E tau by m, and we are dividing it by E. So E and E gets cancelled and the mobility's equation becomes E tau divided by m. So that is the equation of mobility. Now let's look into the relation between current, which is I, and drift velocity, which is Vd. So the relation between current and Vd. So for that we are taking a conductor and it is connected externally to an electric field or a terminal. Now the length of this conductor is L, the area of this conductor is A, the number of charges that are present in the conductor is small letter n, and it is driven by the electric field E. So in order to find the volume of conductor, I just have to multiply the area and the length. So volume is equal to A into L. Now if I am going to measure the total charge that is present in this conductor, which is represented as capital N, then N is equal to the small letter n into volume. So it's N into AL. Now we know from the condensation of charge that Q is equal to NE. We know that current is equal to the charge by time. So Q by T is the equation of current, and instead of Q I am writing NE by time, where N is equal to NAL. So NALE by time. Here you can see that L is the distance of this particular conductor and time is the time taken to travel this particular charge. So L by time, that means distance by time gives the velocity. So instead of distance by time, I can write it as drift velocity, and the relation between the current I and Vd is I is equal to NAVDE, where N is number of charges, A is the area of the conductor, Vd is the drift velocity, and E is equal to 1.6 into 10 raised to minus 19 coulomb. So that is the relation between current and drift velocity. Very important relation, need to learn. Okay. Moving on, let's look into one more term, which is current density, and current density is represented as J. So current density is the amount of electric current that is passing through a particular cross-sectional area. If I am taking a particular cross-sectional area, I will be looking the amount of charge that is flowing through that particular area. So J can be represented by I by A, and we know that the equation of I is equal to NAVDE divided by A. A and A gets cancelled and we get the equation of J to be VDEN. Clear? Now we know that Vd is the drift velocity and it is equal to E tau by m. Now reducing at E into E square, so NE square tau by m into E is the equation of current density, and these all are constant and E is the only thing that is varying, so we can term it as a constant, and that constant is called conductivity, and conductivity is the ability of a material to conduct electrons. So how is current density related to conductivity? Current density is equal to conductivity into electric field. So these are the terms that you have to focus on electric current. What all are the things that we have learned? What is electric current? The drift velocity, the mobility, the current density, and the relation between current and drift velocity. So what is Ohm's law? Ohm's law is a law which was proposed by G.S. Ohm in the year 1828, and it is related to the flow of current. So Ohm's law is a law that is connecting potential difference V, current I, and resistance R. So according to Ohm's law, the flow of current, that means I, is directly proportional to the voltage, the potential difference. So we can write V is directly proportional to I. Okay. Now consider a resistor and a current is passed through this resistor and the potential difference between the two ends is V. Then we can write V is equal to IR. This proportionality is cancelled by a constant R, and R is called the resistance and its SI unit is Ohm. So this is Ohm's law. Now Ohm's law shows you the fact that both V and I are directly proportional. So we can draw graphically the relation between V and I, and the graphical representation is called VI characteristics. Means V will be taken in the x-axis and current will be taken in the y-axis, and we will be drawing the lines and we will get a straight linear line in case of materials that follows Ohm's law. Okay, so these are the ideal materials that follows Ohm's law, and we will get a straight constant line if a material is following Ohm's law, because in that case V and I will be directly proportional. The examples of such materials are carbon resistors, metals, etc. Okay, so these are the examples of materials that exhibits Ohm's law. But Ohm's law isn't always expressed as it is, and different material have different characteristics, VI characteristics, and they show non-linear VI characteristics. So the three examples of materials that show non-linear VI characteristics is shown here. The first one is good conductors. They actually show a relation, a constant relation or a constant slope between V and I, but after a certain point there is a certain deviation. So it is the first condition. The first condition is V ceases to be, actually act as it is proportional to I, but there is a certain small deviation. Now the second example is in the case of diode. In the case of diode, if we are reversing the voltage, for the positive voltage it exhibits one type of current, and for the negative voltage it represents another type of current. So we have two values of current for positive and negative. So the relation between V and I is dependent on the sign of V in the case of diode. Now in the case of semiconductors, consider this particular point. This particular point is corresponding to 3 ampere for example, and we have 2 volt here, but the same line will also give, or 3 ampere will also produce 10 volt afterwards for example. So we do not have unique values. So that is the third condition where VI characteristics is not linear. So the relation between V and I is not unique in the case of semiconductors. So these are the 3 examples where Ohm's law is showing a deviation with respect to the materials. So learn these 3 conditions and the corresponding graphs. Now let's deduce Ohm's law from drift velocity. So for that I am taking the relation between electric current and drift velocity, which is NAVDE. I is equal to NAVDE, where VDE is the drift velocity which has the value E tau by m. So I am using that equation over here. So I got the equation of current to be NAE square E tau by m. Now here the electric field can be represented as voltage per distance. So we can write electric field as V by L. Now our equation is V is equal to IR. So V is here, I is here. So I am taking all the remaining terms across here, and I got V is equal to IML NE square A tau. Now these values other than I is the resistance. So we got the value of resistance to be ML by N E square A tau. So that is the equation of resistance. From this equation I can say that resistance is directly proportional to the distance L, and it's also inversely proportional to the area. So all the other terms other than L and A are constant, m, n, e square, tau, and that values are taken as rho. M by n e square tau is equal to rho. So that is the value of rho. We have learned in the current density that sigma is equal to n e square tau divided by m. So look at these two equations. From these two equations you got the value. This is the conductivity and this is the resistivity. From these two equations you identified that conductivity and resistivity is inversely proportional. So the reciprocal of resistivity is the conductivity, or sigma is equal to 1 by rho. Similarly, the reciprocal of resistance is called conductance, which is G is equal to 1 by R. So higher the conductance, lower will be the resistance of a material. Higher the conductivity, lower will be its resistivity. So that's about how we deduce Ohm's law from drift velocity. Now let's look into two more terms. They are electric power and electric energy. So why power and why energy? Consider a terminal with plus and minus charge. It produces two voltages across the point A and point B. The voltage across A is taken as VA and voltage across B is taken as VB. So the work done to take a charge from A to B, move the charge from A to B, is the work taken here. So we can write work is equal to Q into VA minus VB, or this is the potential difference which can be represented as V. So W is equal to QV. Okay. So we got the equation of W to be QV. Okay. Now the equation of power is work by time. So work is QV. So QV by time is the equation. We know that Q by T is equal to I. So we got the equation of power to be VI. But we also know that V is equal to IR. So instead of V, I can write IR into I. So equation of power becomes I square R. So we got two equations for power, IV and I square R. Also, from this equation, I can write I is equal to V by R. So this equation turns to be P is equal to, instead of V, I will put V itself, instead of I, V by R. So equation becomes V square by R. So that is the third equation. These are the three equations of electric power and its work by time. So the unit is joule per second. Now in case of energy, energy is the power into time. Okay, energy is the work used here. So every equations that we obtained, we should just multiply it by time. So instead of IV, the work will be IV into T. Instead of I square R, the work will be I square RT. Instead of V square by R, the equation is V square by R into T. So joule per second will be not there, joule only will be the unit of energy. So these are all about electric power and electric energy, and these is all about Ohm's law. And the most fundamental law of current electricity is Ohm's law, which gives the equation V is equal to IR. In this equation, R is the new constant that has been formed, and in this particular video, we will be elaborating the relevance or the significance of R. So what is R representing? R represents the resistance, or it is the ability of a circuit to prevent the current flow. So resistance is used as an opposition to current flow in an electrical circuit. So we know the equation V is equal to IR. From that we can mathematically represent R is equal to V by I. The SI unit of resistance is ohm and it is represented in electrical circuit as here. Okay, it can also be represented as this when it's variable resistance. Okay, now we know that from the previous video we have been learning that R, the resistance, depend on the dimension of the conductors. Number 1, it depends on the length. So consider I am taking a conductor and I am increasing its length by twice. Then its voltage will also increase by twice. So we get 2 voltage here. Okay, so what happens? Our equation is R is equal to V by I. So instead of V, we can write it as 2V by I. That means 2 into resistance. So when we increase the length, the resistance is also increased. So resistance is directly proportional to the length. Now let's look into the second dimension where resistance depend on, and it is the area. Okay, consider I am taking a conductor. I am dividing the conductor into 2. So I am reducing the area. I am decreasing the area here, and let's see how it impact on the resistance. So here I am cutting the conductor into 2, and what happens is corresponding current will be also turned into half. Okay, so our equation is R is equal to V by I. Instead of I can write it as I by 2. So 2 comes up and I got 2 into R when the area is reduced. So when area is reduced, resistance is increased. So resistance is inversely proportional to the area. Okay, so we got that resistance is directly proportional to length and it is inversely proportional to area. So in order to remove this proportionality, we are introducing another constant, and that constant is called electrical resistivity, and it's denoted by rho. Okay, so electrical resistivity R is equal to, or electrical resistivity cancels this particular constant and we get R is equal to rho into LA. From this I can write electrical resistivity as RA by L. Okay, so resistivity is the fundamental property of a material and it represents how it can prevent or resist the electric current. Now from Ohm's law, we reduced the value of rho. Rho was M by NE square tau. Now the SI unit of electrical resistivity is ohm meter. Now this is all about electrical resistivity. Now if a material does resist the electric current, what does that mean? It is highly electrical resistive. But if a material has high conductivity or will allow the flow of electrons through it, then we call they are highly conductive, and the corresponding representation as electrical conductivity. It is the ability of a material to conduct electricity and it is represented as sigma. So when resistivity increase, conductivity decrease. If conductivity is increased, resistivity is decreased. So we can write that conductivity is the reciprocal of resistivity. It is the reciprocal of resistivity. So we got here rho is equal to RA by L. So sigma will be L by RA. Clear? So that's all about electrical conductivity. Now let's analyze different materials on the basis of resistivity and conductivity. Yeah, conductors are good in electron flow and it exhibits high conductivity. In the case of semiconductors, it exhibits both conductivity and resistivity moderately. And the case of insulators, it exhibits high resistivity because it will not allow any electron to flow through them. So that is the three classification of materials based on conductivity and resistivity. Moving on, we are going to look into a special device that uses the application of resistance, and such devices that are used are called resistors. So it's a device that is used in electric circuit in order to adjust or in order to maintain or in order to prevent the current flow. It's also used for safety purpose. So basically there are two types of resistors that are being commonly used. Number one, carbon resistor, and number two, wire wound resistor. Carbon resistor consists of a long range. So it consists of long range of order, but in the case of wire wound, it's low range ohms, okay, 10, 12, etc. Now, carbon resistor exhibits low stability, or it gets damaged very fast, okay. So that is a disadvantage of carbon resistor. But in case of wire wound resistor, they exhibit high stability. Now, carbon resistor is smaller in size and lightweight, and it's commonly used in electronic circuits, and we are using it for lab purposes and everything. But in case of wire wound resistor, it is bigger in size when compared to the carbon resistor. Okay, now looking into the figure, you can understand that there are certain rings that are present in this resistors. So these rings are representing certain color codes, and that color code corresponds to the value of this particular resistor. So let's see how we can determine the value of a resistor using the color code or using the ring. For that, you have to learn a table, and this is that table. Now, in order to easily learn this table, I am here with an easy way. Okay, look into it. B.B. Roy of Great Britain has a very good wife. Learn this mnemonic so that you will be learning this color in its order, and you have to learn it in order in order to easily analyze the color code. Okay, so B black, B brown, R red, orange, yellow, green, blue, violet, grey, and that's how these 9 colors are coming into action. Now, the rest of the 3 are not coming in the color code. This represents the tolerance. Okay, so this you have to learn by heart. Okay, now in this you have to learn this order also. So, black represents 0th number, red represents 2, grey represents 8, etc. Now, the 3 tolerances are gold, silver, and no color. Gold represents 5%, silver represents 10, and no color represents 20. Okay, now let's see how we can apply this color code into determining the value of resistor. So, this is how a resistor will look like. It will be consisting of 4 coaxial rings. Out of this, the first 2 rings represents the digit. The third ring will represent the number of 0 of that particular digit. And the last represents the tolerance, which is determined by these 3. Clear? Okay. Now let's look into an example so that you can easily understand how we can value or how we can measure a value from this resistance. So for that, here you can see 3 red color and 1 silver color. Okay, just as the figure indicates, the first 2, that is 1, 2. The first 2 represents the digits. So we have to just put the number corresponding to it. Red represents 2. So I will be writing 2, 2. Into the third represents the number of 0. So 10 is representing as the base, and red represents 2. So 10 raised to 2. Plus or minus, the tolerance level is silver, so it is 10%. Similarly, here yellow represents 4, violet represents 7, brown represents 1, so 10 raised to 1, and gold represents the tolerance level. So this is how we measure the value of resistance from this particular color code. The resistivity of a material is dependent on its temperature. That means if temperature is increased or decreased, it will affect the resistance of a material. So this is represented by a mathematical equation as shown, which represents rho T is equal to rho 0 into 1 plus alpha into delta T. Delta T represents the temperature difference that is obtained. Alpha represents the temperature coefficient. Rho 0 represents the resistivity at 0 temperature and Rho T represents the resistivity at T temperature. Now, here the most important term is the temperature coefficient, and it is positive in case of metals and negative in case of semiconductors. Moving on, let's analyze some of the graphs on the basis of temperature and resistivity. So these three graphs represents three different materials and their temperature dependence. Okay. So in case of conductors, you can see that when the temperature increases, the resistivity is increased exponentially. Now in case of alloys, you can see a linear increment as the temperature increases. So when temperature increases, resistivity of alloys also increase. Now in the case of semiconductors, it is just the opposite of conductors, that is, as the temperature increases, the resistivity will decrease, indicating the semiconductor will travel from insulator to conductor. It will change to conductivity when the temperature is increased. So these are the three graphs that represents the variation of temperature with resistivity. Now, if you are considering or analyzing a complex circuit with many number of resistors that are placed on it, we have to analyze it in a different way. Consider the resistors are connected in series. So here you have three resistors R1, R2 and R3. They are connected in series and it is given an external terminal supply. Now in series connection, the voltage will be always different and the current will be always same. So the voltage across R1 is V1, the voltage across R2 is V2 and the voltage across R3 is V3. Okay, so we know that V is equal to IR. So we always should start any derivations based on series when considering the different point. Okay, so here V is different, so we have to write V is equal to IR. That means V is equal to V1 plus V2 plus V3, or we can represent IR is equal to IR1 plus IR2 plus IR3. I gets cancelled everywhere, so we get when resistors are connected in series, which is represented as RS, we just have to sum up all these resistors to get the final total resistance of the circuit. Now, if the resistors are connected in parallel, just as shown here, you have three resistors R1, R2 and R3 and they are parallelly connected to a terminal. Here the voltage will be same, okay, because voltage is here VA, VB, so voltage will be same. Voltage is the potential difference, it's same, but the current will be different for different loops. So current is different. So start with current. So we know that I is equal to V by R. So V by R is equal to V by R1 plus V by R2 plus V by R3. V gets cancelled everywhere. So we get, if resistors are connected parallelly, we just have to take reciprocals of each of these resistors and just sum it up. Then that gives the connections or total resistors that are connected in parallel. So this is how we analyze the total resistance of a circuit if it's connected in series or in parallel. And the simplest circuit that is made to analyze current electricity is comprised of terms like cells, EMF and internal resistance. So these are the terms that you are familiar with because you have been studying the same in electrochemistry. So moving on, we will be looking into this definitions with respect to the physics aspect here. Okay, the first one is cells. So what are cells? What is an electrolytic cell? Cell is the simplest device that is used in an electric current or electric circuit in order to produce a steady current. The simplest device can be represented as a cell, or we can call it as an electrolytic cell. So electrolytic cells consist of a container with electrolyte solution. Two electrodes are present over here. One is negative and one is positive. The negative electrode is called cathode and the positive electrode is called anode. So anode is positive, cathode is negative. Okay, so this will create a potential difference, and they are externally connected via a resistance which is represented as capital R. So cell is a device that maintains a steady current, and there is a potential difference that is occurring in a cell. We can symbolically represent the same electrolytic cell as a circuit diagram as follows, and these represents the cell over here. Okay, now the second term, which is EMF or electromagnetic force. So EMF is the potential difference that is happening across these two electrodes that are present over here when we are not using or when no current flows through it. So when the current is 0, how much potential difference is this electrode providing? That is the EMF. So EMF is represented as epsilon, but we call it E itself. It is the potential difference of the anode plus the potential difference of the cathode with no current flowing across it. So that is the second term, EMF. Now the third term is internal resistance, which is represented as small letter r. So internal resistance is the resistance provided by the electrodes. So it's not externally produced, it's provided or it's inbuilt in the electrodes. Okay, now I have to mathematically represent a internal resistance. So for that I am taking the total voltage across an electrolytic cell. Okay, so the total voltage of electrolytic cell is taken as capital letter V. It is produced by the EMF over here minus the current across the internal resistance. So minus IR is the current across the internal resistance, because internal resistance opposes the total EMF produced. So V plus V minus IR. Okay, so V plus V minus is represented as EMF E, or we can take this second term over here. So we get the equation of EMF to be E is equal to V plus IR. Well, V is the current across this particular resistance. So we can write it as IR into R. Here I is common, so I is taken outside, and we are just taking this reciprocal over here. So we got the equation of current to be E divided by R plus R. So we were only expecting the change in EMF with respect to the capital resistance, but there is a small resistance that come into action which is affecting the current. So we have to take into account that too. So that is the internal resistance. Now internal resistance varies on different aspects, or it's dependent on different aspects, and let's look what are those. It's dependent on the nature of electrode or the material of electrode that we are using, and it is dependent on how concentrated is the electrolyte or the solution where the electrodes are immersed. It's dependent on the temperature. Okay, temperature, we know that resistance and temperature are dependent. So it's dependent on the temperature. It is dependent on the distance between these two electrodes. So this distance is in action. So it affects the internal resistance. Also, it's dependent on the relation between the electrodes. If electrode is like this, and this is the solution electrolyte. So it's related to the how immersed the electrodes are with respect to the electrolyte. So these are the things internal resistance are dependent on. Now let's analyze what happens when cells are connected in series or when cells are connected in parallel. What happens to the corresponding or equivalent EMF and equivalent internal resistance? So that is what we are going to divide. So the first condition is cells are connected in series. So here you can see two cells, E1 and E2, with internal resistance R1 and R2 respectively, and they are connected in series. This particular circuit can also be drawn as this, and we are going to find what is E equivalent, or what is the representation of E equivalent, and what is the representation of R equivalent over here. So we know that in the case of series connection, voltage turns to be different and current turns to be same. So I have told you what is different. You have to equate or start derivation on the basis of that. So V is equal to V1 plus V2 over here. We know that the equation of V is E minus IR, where R is the internal resistance and E is the EMF. So in case of, first this is voltage over here and this is the voltage over here. So in the case of V1, the equation becomes E1 minus IR1, and in case of V2 it's E2 minus IR2. Now I am combining the terms of E1 and E2 together, and I am combining these second two terms together in order to equate it with respect to this equation. So instead of V, I can write it is EEQ minus IREQ, and hence the follows. Okay. Now E1 plus E2 is taken as 1 minus I into R1 and R2 is taken as 2. Now from this equation, so this is the equation that we finally obtained, and from this equation EEQ is equal to E1 plus E2. We should compare both the sides. I is not taken, REQ is equal to R1 plus R2. So that are the equations of equivalent EMF and equivalent resistance in the case of cells that are connected in series. Now what happens when cells are connected in parallel? For example, here you can see two cells E1 and E2 that they are connected in parallel, and the corresponding resistance, internal resistance over that is small letter R1 and small letter R2. In the case of parallel connection, the current is different and the voltage is same. So we will be focusing on the equation of current. So we know that V is equal to E minus IR. So I can write the equation of IR to be, or I to be, E minus V by R, or V equivalent is equal to E equivalent minus IR equivalent. So these graph of this circuit can be drawn as this, and we are going to analyze E equivalent and R equivalent. Okay, so taking this into action. E1 minus, we know that the current over here, this is I1, and the current over here is I2. So I is equal to I1 plus I2. Okay, so we have the equation of I is equal to E minus V by R. So E equivalent minus V by R equivalent is equal to E1 minus V by R1 plus E2 minus V by R2. This represents current I1, and this represents current I2, and this represents the total current I. Clear? Now I am taking, just as before, I am taking the terms of E1 as one side and taking the values corresponding to V as another side. So I can write E1 by R1 plus E2 by R2 first, minus V into 1 by R1 plus 1 by R2. Okay, now here this is the general equation that we have. So we have to convert this particular equation with respect to this. So we need to find the value of V equivalent on the one side. So what I am doing is I am going to take the terms related to it on the other side. Before that, I am going to cross multiply it. So E1 R2 plus E2 R1 divided by R1 plus R2, R2 plus R1 divided by R1 R2. Now this term is taken here, over here. So I got E1 here becomes reciprocal. So I into R1 R2 by R2 plus R1 is equal to E1 R2 plus E2 R1 divided by R2 plus R1 minus V. Now I want to equate it with respect to this. So comparing these two equations, what I have to do is I should take V over here and this equation over here. So I get V is equal to E1 R2 plus E2 R1 divided by E1 plus R1 plus R2 minus I into R1 R2 divided by R1 plus R2. Okay, so we have the equation V is equal to E equivalent minus I R equivalent. So comparing these two, I can write E equivalent is equal to E1 R2 plus E2 R1 divided by R1 plus R2, and R equivalent to be R1 R2 divided by R1 plus R2. So this is the equations of internal resistance and EMF when we are considering the cells that are connected in parallel. So Kirchoff's rules are the rules which make the complex circuit into the simpler one. So let's see what are Kirchoff's rules. So Kirchoff's rules basically make or analyze the complex circuits, and it determines the current and the potential difference of the voltage. Basically, Kirchoff's rules is divided into two. The first one is Kirchoff's current law, or we call it junction rule. The second one is Kirchoff's voltage law, or we call it loop rule. So let's look each one of this one by one. So the first one, Kirchoff's current law or the junction rule. So for that, we are going to consider a junction. This point is a junction. And we are going to analyze the current over it. Consider the junction J, and I1, I2 and I3 are the currents that are incoming to this particular junction. And their corresponding resistors are R1, R2, R3. Now, from this junction, consider I4 and I5 are leaving this particular junction. Then according to Kirchoff's junction rule of this particular junction, we can say the sum of current entering the junction is equal to the sum of current leaving the junction. So here I1 plus I2 plus I3 is the current entering, and I4 and I5 are the current leaving. So current entering is equal to sum of the current entering is equal to sum of the current leaving. So that is the first rule. Now we can analyze this rule in a different way. Consider this particular equation. If I am taking these two values over here, I can write it as I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. So that's another definition of junction rule, which is the algebraic sum of all current entering and leaving a junction is 0. What does that mean? No current will stay in this particular junction. The current passes continuously. So that is the law, which is the Kirchoff's current law, and it proves the conservation of charge. So learn these 2 points. Now the second law is Kirchoff's voltage law, or we call it loop rule. So for that, we are going to consider a circuit. It has 2 loops, L1 and L2. According to Kirchoff's voltage law, the algebraic sum of product of current and resistance, that means if this one loop has 2 resistance and their corresponding current is I1, then the algebraic sum of product of resistance and current, okay, is equal to the EMF of that loop. It will be the EMF. So we can mathematically write this equation as sigma E is equal to sigma I into R. Okay, now let's apply loop rule into this particular figure or into this particular circuit diagram. Here you have 2 loops, L1 and L2. In both of this loop, R2 is common. We have 2 EMFs, E1 and E2. Now E1 produce current I1, which will pass this way. Okay, so R2 have current I1 and R1 also have current I1. Similarly, E2 will produce current I2, which is going this direction, positive to negative. So R2 also have current I2 and R3 also have current I2. So R2 is common for both I1 and I2. So we can write it as I1 plus I2. So let's equate this particular loop with respect to current Kirchoff's voltage law. So we can write E1. E1 is the sum of the currents across the resistance. So here there are 2 resistance, R1 and R2. Across R1 there is only I1. So I1 into R1 plus I1 plus I2 into R2. So that is the equation of E1. Similarly, in case of E2, we can write R3 into I2 plus R2 into I1 plus I2. So these are the two equations of EMF of this corresponding loop. So that's how Kirchoff's voltage law works, and that's how we get similar equations for the circuit, the complex circuit given. Okay, so that's Kirchoff's voltage law. So I hope you understood what is Kirchoff's current law and what is Kirchoff's voltage law. So based on these Kirchoff's rules, we can work out into another circuit, or we can apply it into another circuit, and the example of applying Kirchoff rule into one circuit is the Wheatstone bridge. So Wheatstone bridge is mainly used to determine an unknown resistance. Okay, consider that you are given a wire or a conducting wire, and if someone asks you to find the resistance of this particular wire, how will you do that? We can do that with the help of the arrangement of Wheatstone bridge. So the use of Wheatstone bridge is to find the unknown resistance. So the unknown resistance that we have is taken as R4, and across it we keep a standard arm. Okay, now this arrangement can be, although this construction can be explained as follows. Here you have 4 resistors, R1, R2, R3 and R4. Okay. Now, they are externally connected to a battery, and in between you can see there is a galvanometer present. So the figure is clear to you. Now here you can see 2 loops over here and over here. So we will be determining the values of these 2 loops separately, and we will be finding the resistance unknown, which is represented as R4. Okay. Now here you have positive terminal and here you have negative terminal. So the current will go through this and current will come back through this. Here the current at the point A, the current is split into 2. So we have 2 currents, I1 and I2. It goes and it reaches, I2 goes and reaches P2 and it goes through R4. And through R1, I1 reaches R3. So we have this diagram. Now, I am going to apply Kirchoff's rule in the first loop. Here you can see both the direction of the current I1 and I2 are different. So I can write I1 into R1 is equal to I2 into R2, or applying junction rule I can write minus I1 R1 plus 0 plus I2 R2 is equal to 0. Now, from this equation I can get the value I1 by I2 is equal to R2 by R1. Okay, so this is the first equation that I obtained from this particular loop. Now look into the case of the second loop, which is CDBC. Here also there are 2 currents I1 and I2 and they are in opposite direction. So I can write I2 into R4 is equal to I1 into R3, or by applying junction rule I can write I2 R4 plus 0 minus, because here we are considering the current across the galvanometer is 0, that is the reason why 0 comes over here, minus I1 R3 is equal to 0. And from this equation I can write I1 by I2 is equal to R4 by R3. So I got 2 equations for I1 by I2. One is here and one is over here. So the 2 equations are over here. Here the LHS is same. So we can write R2 by R1 is equal to R4 by R3. Here the unknown resistance is R4. So taking R3 over here, I can write R4, the unknown resistance R4 is equal to R3 into R2 by R1, and that's how I will find the value of this unknown resistance. Here the circuit undergot Kirchoff's rules to make it easier. So that's how Wheatstone bridge works, and this derivation is pretty simple. And that's how this chapter ends, and we will be seeing in the next video with a new chapter. Until then, bye.